Hello everyone and welcome back to my channel Gyan Sampada. In our previous classes, we were dealing with the PN junction, energy level diagram and also the potential barrier. And today we will study about the barrier thickness, that is the width of depletion region. While studying the PN junction, in detail we have dealt with the depletion region, how it is formed, what is the phenomena which is occurring, based on which we can understand about different parameters. And making use of our previous knowledge only, we are going to derive the equation for width of depletion region. Depletion region is also called as space charge region, which is going to act as the barrier in between P region and N region of the junction. And this can be also called as barrier thickness. So barrier here is the potential barrier, that is of course the space charge region. We have already seen that the space charge on N side is positively charged, whereas when you compare it with the P side, it is negatively charged. So our concentration is mainly on depletion region. If you consider PN junction, this side is a P side, this side is N side, and here we can observe negative charges, whereas here we observe positive charges. And in this depletion region, we can say the extent is from x1 to x2. So negative sign shows it is in negative x direction. Then totally the space charge region or depletion region extends from x1 to x2, which is denoted by x, which is nothing but x1 plus x2. So here x1 and x2 are the widths of the space charge region in P and N sides respectively. And we should know that the area of the depletion region in each region is going to depend on the concentration of impurities in this region, that is the carriers which are present there. And we know that in the depletion region the potential is going to vary something like this, where on the P side we have taken the potential as minus V1 and on N side it is taken to be V2. And the total potential barrier will be sum of V1 and V2, which we had denoted as VB, that is the barrier potential. And in our previous class, we have derived the expression for the potential barrier with respect to the concentration of charges. And today, we are going to derive the barrier thickness or width of the depletion region, that is nothing but x. So clearly from this diagram we can say x is equals to x1 plus x2, and here x1 and x2 can be understood based on V1 and V2, which gives us the potential barrier. So our steps are straightforward. First we will deal with the potentials, based on which we can find out what is x1 and x2. When we take the sum of both, we get the barrier thickness. And in order to find out the effective area of depletion region, we need to take the help of Poisson's equation. And the Poisson's equation states that the second derivative of potential with respect to the distance is proportional to the charge density, that is rho, or it is said that it is equals to 1 by epsilon naught times of the charge density. So in equation number 1, V is the potential, rho is the charge density in the material, and epsilon is the permittivity of the material. And this is the Poisson's equation in one-dimensional simple case when the voltage is going to vary with respect to the x direction, that is along the length of the crystal. Then we consider a portion of the depletion region which is situated in the P region near the junction. So first we will go with respect to this region and then we will move on to this region, which are going to be almost analogous to each other. So considering first region where we will find out finally x1. So here the charge density can be written as rho is equals to minus E Na, which we are calling as equation number 2, where Na is the density of acceptor atoms. And here, what is the significance of the negative sign? So it just shows that the acceptor atoms are negatively ionized. So applying Poisson's equation in this region, that is substituting equation 2 in equation number 1, in place of rho we have substituted minus E into Na. So minus of minus will become plus to get d square V by dx square is equals to E Na divided by epsilon. Call it as equation number 3. As I told you, if we need to understand about x, we need to know x1 and x2. For that we need to know v1 and v2, based on which we can find out vb. So here we can observe there is a term of potential, and if we need to find out what is the value of v, we need to double integrate it. So first on integrating we get dv upon dx is equals to ENA by epsilon is a constant into x plus a, where a is the integration constant, and further again we need to integrate so that we obtain v, which will be equal to ENA by epsilon as it is. Integration of x is x square by 2 plus integration of a is a into x, that is integration of a constant or 1 is equals to x itself because the domain is with respect to x, plus b, which is again the integration constant, and we are calling it as equation number 5. Remember that a and b are the arbitrary constant, and if we find out what are the values of a and b, we can tell what is the value of v. So here first we have considered this region that is extending from 0 to minus x1. Here the boundaries are 0 and at x1. So what happens at 0? When x is equals to 0, we observe that v is also equal to 0 here, and when x is equals to x1, we observe that v is a constant. So next, in order to find out the integration constants, that is a and b, we will make use of the boundary conditions. So first one, what happens at the origin? So at x equals to 0, we can say v is equals to 0, or at v is equals to 0, we have x is equals to 0. That is evident from the previous diagram. And we need to substitute this in the previous equation, that is equation number 5, we get b is equals to 0. Because when you substitute x values, first and second term in the RHS part is going to be equal to 0, and we obtain that b is equals to 0. And then applying boundary condition number 2, that is in P region, we know that the potential is going to remain constant throughout. So V is constant, and whenever V is constant with respect to the position, its change is 0. So V is constant means its derivative with respect to x is 0 when x is equals to minus x1. That is at the boundary of P region. And now substituting the values in equation number 4, we get dv by dx is equals to ENA by epsilon into x plus a, because here we have found out the value of b and then we are going to find out the value of a. So substituting the value of dv by dx, that is equals to 0 when x is equals to minus x1, substituting we get a is equals to ENA x1 divided by epsilon, because when this negative sign is taken on LHS side, it becomes positive. So finally, making use of boundary condition, we have found out the values of integration constants. Then we need to substitute the values of a and b in equation number 5, which gives us the value of v. So v will be equal to ENA by epsilon x square by 2 plus, in place of a, it is ENA by epsilon into x1 into x plus b is 0. And when we put the values of v as minus v1, that is in the P region, and x is equals to minus x1, Then the above equation becomes minus v1 is equals to the constant as it is. In place of x we have minus x1 whole square, and in place of small x we are substituting minus x1 again. So x1 into x1 will become x1 square, and when we simplify it we get the value of v1. So both are almost same, that is ENA by epsilon into x1 square, ENA by epsilon into x1 square. So when you take it common, in the bracket we are remaining with 1 by 2 minus 1, which will be minus 1 by 2. So here minus 1 by 2 is written, and negative negative will get cancelled, finally leading us to v1 is equals to ENA by 2 epsilon into x1 square, which we are calling as equation number 8. So this is one part, and in the similar way the Poisson's equation may be applied for the portion of depletion region situated in N region near the junction. So again, considering that the charge density in this region is due to the positively ionized donor atoms, where charge density can be given as rho is equals to E into Nd. Nd is the density of donor atoms, which can be substituted in the Poisson's equation for this portion of depletion region, which gives us equation number 10. Then again, to find out V value, we integrate the above equation. So on first integration we get a integration constant C, then again integrating we get V is equals to minus E and D by epsilon into integration of x is x square by 2 plus C, integration of 1 is x plus D. So earlier we had A and B, now the integration constants are C and D, and in the same manner we are going to find out what is the value of C and D. So making use of boundary conditions again towards the N region of the junction. So when V is equals to 0 and x equals to 0, we get D is again equal to 0, that is substituting x value and V value, and at the N region boundary we have V as constant. So dV by dx will be equal to 0 at x equals to x2, that is right side of the depletion region. And again substituting back this into equation number 11, we get the value of C as E and D by epsilon into x2, which we call as equation number 14. So now we have found out the values of C and D, so we need to substitute it back in equation number 12, which leads us to the value of V. Then we will put V is equals to V2 and x equals to x2 in the above equation, through which we get the value of V2 as E and D by 2 epsilon into x2 square, which we are calling as equation number 15. So now we have found out what is the value of V1 and V2, that is the potential at x1 and x2 respectively, which are the boundaries of the space charge region, or we can say ends of the space charge region. And making use of this, we can find out the barrier potential, and the potential barrier at the junction will be equal to Vb is equals to V1 plus V2. Putting the values from equation number 8 and equation number 15, we can observe that E divided by 2 epsilon, E is constant, taken outside the bracket, and we are remaining with NaX1 square plus NdX2 square. And this is the value of potential barrier with respect to the length of depletion region. And of course, it is going to depend on the density of the donor and acceptor atoms. Let us call it as equation number 16. Remember, in previous class also we understood about the potential barrier, but the expression there what we had derived was with respect to the electron concentration and hole concentration. But here now it is with respect to x1 and x2. Then after finding out Vb, we need to find out the value of x1 and x2. And in order to know about the barrier thickness, we consider the charge neutrality condition, that is something like the balancing condition, which is given as E Nd x2 is equals to E Na x1. So rearranging the equation to get x2 in terms of x1, E will get cancelled and x2 will be equal to Na by Nd times of x1. And then we will substitute the value of x2 from above equation to the barrier potential equation. So Vb will be equal to E by 2 epsilon as it is, Na into x1 square as it is, plus in place of x2 square we are substituting Na by Nd x1 whole square. And simplifying this equation, we can see that x1 square is common, which can be taken outside, and also 1 Na can be taken outside. We are remaining with 1 plus Na by Nd, because Nd square in the denominator, 1 Nd will get cancelled from the numerator. And then easily we can rearrange this equation to get what is x1. So x1 square will be equal to 2 epsilon Vb divided by Ena into this bracketed term. So x1 square is there, taking the square root, we observe that x1 is equals to square root of 2 epsilon Vb divided by Ena into 1 plus Na by Nd. And this is the equation for width towards the P region in terms of the barrier potential and the charge density. And this equation is named as equation number 18, and based on the same we can also find out x2 value, that is substituting the value of x1 in equation number 17. So in place of x1 we are substituting this value, then we need to simplify. So here Na is taken to the denominator, so it will be 1 divided by Nd by Na, so that we can take this inside the bracket. So as there is a square root, this term is going to get squared when it goes inside, and clearly we can observe that 1 Na is going to cancel out and we are remaining with Nd square by Na, and when we take 1 Nd by Na within the bracket, we can observe that it will be Nd by Na plus Nd by Na into Na by Nd. So that will cancel each other. We are getting 1 here plus Nd by Na. So here we can observe that 1 Nd is remaining outside, and in place of Na by Nd we will get Nd by Na. So this is just a simplification by which we obtain the value of x2, which is named as equation number 19. Now final step is to find out the barrier thickness. So we know that the barrier thickness is x, which is the sum of x1 and x2. Already we have found out the values of x1 and x2 in previous slides. So substituting those values, we can observe that square root of 2 epsilon Vb divided by E is common in both the terms. So we can take that common, and also the bracketed term in the denominator we can simplify here as Nd plus Na divided by Nd, and here it has Na plus Nd divided by Na. So taking the common terms outside the bracket, that is 2 epsilon Vb divided by E into Na plus Nd or Nd plus Na, both are same. Then from the first term we are remaining with Nd goes to numerator divided by Na raised to 1 by 2 plus here Nd remains in the denominator, Na goes to numerator, so raised to half. Then again we can simplify this further, that is taking LCM here. So LCM is Nd into Na raised to half. Here we are already having Na raised to half, Nd raised to half is missing, so multiply by Nd raised to half, we get Nd in the numerator. Similarly here we get Na. So Nd plus Na divided by square root of Na Nd is the simplified version, and clearly we can observe that Nd plus Na and Nd plus Na raised to 1 by 2, one root is going to get cancelled. So finally we are remaining with square root of Nd plus Na divided by NaNd, which can be written as square root of 1 by Na plus 1 by Nd. So if you simplify here, we can observe NaNd, and in the numerator Nd plus Na. The same thing we are observing here. And this is the equation for the barrier thickness. So here X, which is considered as barrier thickness, is expressed in terms of barrier potential and also in terms of Na and Nd. And thus we can say that the width of the depletion region can be easily determined if the value of potential barrier Vb and the densities of donor and acceptor atoms in n-type and p-type regions of the p-n junctions are known. And this is the derivation which gives us the value of thickness of depletion region. As such, the derivation may look lengthier, but the same steps are repeated. Once we find out what happens in the space charge region which is near to p region, and then the similar steps are done for the depletion region near n region. So finding out the potential barrier and then expressing x1 and x2 in terms of Vb, and simplifying we get the final expression for x. So these are some of the details about the width of the space charge region in terms of potential barrier. And in our next class, we will be dealing with the junction capacitance and its determination, how it is done. So just practice this derivation to understand more precisely, and see you in our next class. Till then, stay tuned, practice well, and thank you.